Hello, so this is going to be our review video for the first lesson in optics. We started by discussing how a crowd wave works. A video in case you've forgotten what I was talking about. And we discovered when we did the crowd wave in class that we were moving our hands up and down, so that was the disturbance in the medium. And the wave was actually moving from left to right, so it was going sideways. So waves are produced by a disturbance in the medium or a field, and this wave is an example of a transverse wave because the direction of motion of the wave, or the direction in which the wave is moving, is at 90-degree angles to where you're doing the disturbance, which is up and down motion. You're moving our hands up and down. So this is the diagram of a transverse wave. There's a couple of important points that we have to note. We have a crest, it's the top of the wave. We have a trough, just the lowest point of the wave. And there are some definitions that we also learned. We learned about what the wavelength is. So the wavelength is the distance between two successive crests, so that's one wavelength as shown here. It can also be the distance between two successive troughs. That is also one wavelength, and it's constant for a given type of wave, right? We also learned about, the wavelength also corresponds to the type of wave, and we also learned about what an amplitude is. So the amplitude is the maximum height of the wave from the undisturbed position. So if the undisturbed position was the red line, the maximum height is from the red line to the crest or from the red line to the trough. Those two distances are equal to each other, and it corresponds to the intensity of the wave. We also discussed what a medium is. So a medium is a substance through which a wave moves. The crowd wave has a crowd as a medium, and an ocean wave has water. There's one type of wave which we're going to focus on for the rest of this, and it does not require a medium to transfer. So it's a special kind of wave that does not require a medium, and we're going to be talking about electromagnetic waves. It does not require a medium because, as we discussed in class, the electromagnetic field is one of the one of many fundamental fields present in the universe, and so disturbances caused in that field cause electromagnetic waves, but they do not require air or water or any kind of medium to travel through. They can travel through empty space because the field exists everywhere, even in empty space, the electromagnetic field. So, what is an electromagnetic wave? It is a wave that is produced by a disturbance in the electromagnetic spectrum, and also it's caused by the movement of electrons. So we learned about what electrons are, and when these electrons move in various types of movements, we'll say, it causes a disturbance. So basically whenever electrons move, there's a disturbance, and we know that disturbance causes waves. We talked about different kinds of waves. So important to stress that all of these waves are technically electromagnetic waves. They're just different types of electromagnetic waves, right? So they have the same characteristics. They're all electromagnetic waves. They can all travel without a medium. They're just different types of an electromagnetic wave, and they differ in their wavelength pretty much. So we'll see that the radio wave that's at this corner over here has a large wavelength, and a gamma wave or gamma ray has a very short wavelength. So these are the smaller wavelength kind of waves. These are the larger wavelength kind of waves, and it goes in descending order of wavelength. So we have radio waves the largest, then comes microwaves, infrared, visible light, which is important, ultraviolet rays, X-rays, and gamma rays. We're also going to split visible light into a section all the way from violet to the red. This is also, just like all these waves are part of the electromagnetic spectrum, all of these colors are part of the visible light part of the electromagnetic spectrum. where the only difference between violet light and red light is the wavelength of the light. So violet light has wavelength around 400 nanometers, and red light over here has a wavelength around 700 nanometers. So, we call ultraviolet light, we call ultraviolet, but it's not technically visible light. Ultraviolet is a kind of EM wave-like visible light, and because it's higher than violet light on the spectrum that we just saw, right? We have visible light over here, and we had ultraviolet right after that. And similarly, infrared is called infrared because it's right before the red, depending on which way you're looking at it. So, again, to stress, the only difference between the waves and the colors is that they have different wavelengths and different frequencies. But they all have the same speed in vacuum. We're going to talk about frequencies next class, but we have to stress that they all have the same speed when they travel through vacuum. All different kinds, like X-rays, gamma rays, violet light, red light, radio waves, all of them travel at the same speed in vacuum, which we said was 300 million meters per second. We also will discuss that we can only see the visible light waves. We can sometimes see UV rays with a special kind of lamp, but we feel and interact with different waves differently, right? So we can feel infrared rays as heat, but we can't actually see the rays like we see light. And we can't see or feel things like gamma rays and X-rays. We can only use them for different purposes. So this was just the homework. So if you have any questions, please let me know. Cheers.